Germany plans to stop using coal for power generation by 2038. However, coal has been mined in the past, and will continue to be mined until the coal phase-out date. And what is left are these damaged landscapes. It would be possible to leave these areas just as they are. But these areas are very unpleasant to look at. They are also very bad for the environment, as nature has been massively destroyed and in some cases contaminated with toxic chemicals. In order to restore these areas, they are renaturalized and can then look as beautiful as they do here in Markkleeberg, south of Leipzig. This also offers the possibility to reuse these areas, for example for recreation and tourism, as a place for renewable energies, such as solar and wind parks, which are two very important technologies to achieve the goals of the Paris Agreement regarding global climate change. Furthermore, these areas can also be used for farming and industry. During the renaturation planning phase, a massive amount of different data is generated, all of which needs to be taken into account into the renaturation process. First and foremost, there is geographic data, such as points and polygon areas, which can be displayed using a geographical information system. This type of data is subdivided into different thematic areas, such as nature reserves, restricted areas, and so on. In addition, these data include information about the areas, such as groundwater levels, a list of all activities that have taken place or are planned, and often also a precise assessment of the animal and plant species for which the specified area is suitable, or was suitable before the mining. Furthermore, there are several text documents, like expert reports and measurement reports, associated with each area, some of which are very extensive. These documents provide information on the different soil layers and indicate where certain chemicals are present, and thus indicate the handling regulations that are relevant for implementation of the renaturation. Legal regulations and requirements that must be observed can also be found here. Next, we also have sensor data and weather data. So we always know what the current conditions are on site. This is important, because some actions depend on certain weather conditions and can only be carried out under particular conditions. Last but not least, nature defines further conditions. For example, some actions are not allowed when certain bird species are nesting. So time aspects must also be included in the planning process. Analyzing the data is tedious and time-consuming. If important aspects are overlooked, the consequences can be fatal. For example, if the soil conditions are incorrectly evaluated, landslides can occur, as shown here. To simplify this work and increase safety, an interactive decision support tool is needed that fulfills all the requirements and is easy to use. The task of renaturation is not new, which is why we have a company as a partner that is familiar with the renaturation of various areas in the region of the Lausitz and central Germany. The company's experts have up to 20 years of experience in field, and therefore we held several meetings with them, where they explained and showed us what data they work with and what their individual work steps look like. One important aspect of their work is the visual comparison of geodata, whereby it is particularly important to get a quick and simple overview among the mass of data. Overlaps between areas are also interesting, because new information can emerge from such overlaps, and restrictions and instructions from one area thus also could apply to the other area. The problem is that the amount of data that needs to be displayed at once, with many things overlapping with each other, quickly leads to visual clutter. This makes the work more complex and time-consuming. So our first goal was to solve this problem. Let me illustrate the problem with some pictures. The experts start with a map on which various data can be displayed. These can be smaller or larger areas, and also simple point data is possible. But as you can see, the more categories there are, the more confusing and unclear the whole picture becomes. The solution so far has been to compare only a few categories, switching them on and off repeatedly to see the differences. There are already approaches to solving the overlap problem. These can be found, for example, in the field of scalar fields, but our dataset is different. There are also approaches based on textures that create certain patterns when overlapped. However, these approaches are limited to a few overlapping layers. Other solutions use mostly point data, or when dealing with areas, they are simplified by single points, such as centroids. Unfortunately, this was not a solution for us as we need to include the whole area and sometimes have very complex polygons. To overcome these limitations and drawbacks, we provide an overview by aggregating overlapping polygons using a quadtree-based heat map visualization. The root of the quadtree comprises the complete area covered by all polygons, and thus represents the bounding box of our dataset. All polygons are linked to the root cell of the quadtree. Then, the root cell is subdivided into 4 quadratic areas, as you can see here, and each of these cells is then further subdivided into 4 quadratic cells, and so on. For each subcell, the system then checks which polygons of the parent cell still overlap with it, and only these are linked to the new cell. Thus, each cell of the quadtree contains information about the number of polygons covered per category. The layer of the quadtree being displayed can adjust it manually or could be linked to the zoom level of the map. So, by zooming in, a finer layer of the quadtree is displayed. For the visual color mapping, the relative amount of polygons overlapping a cell is mapped to the saturation, while the hue is set to red. With this visualization, a good general overview of the distribution of the data is obtained. But how to use this heat map? As our experts often need to check areas for overlap, I will show you the whole process using an example. So there are areas released for later use. These are the areas in the background here in this image. The idea is to check whether one of these areas is suitable for building an amusement park. To keep things simple, there are categories that immediately prohibit certain activities and uses. This means that if the area overlaps with one of these categories, it will not be considered. To check this quickly and easily, the heat map can be filtered to show only these disqualifying categories. Disqualifying categories include nature reserves, general restricted areas, and still contaminated areas. As you can see here, this greatly simplifies the heat map, and since many of the green areas completely contain a cell of the heat map, there is clearly a disqualifying category that overlaps with the area, so almost all target areas are eliminated. But the area in the upper right corner is only covered at the edge. By zooming in, it can be seen that the area is only covered at one point. Since the visualization is interactive and each cell always indicates which polygons it contains, we can also simply select one cell. In doing so, the underlying polygons of the cell are displayed, and we see that they lie outside the green area. Thus, there is no direct reason for rejecting this target area. In summary, we followed the information-seeking mantra, where an overview is provided by this aggregated representation of overlapping polygons. Then, by zooming and filtering, the resolution could be adjusted, and last, the important details are provided on demand by selecting single cells. In the end, we performed a usability study. This study showed that the solution presented was good and was also well received by the users. On the other hand, a few experts were not quite clear at first how they could use the heat map and did not immediately understand how to read and interpret it. This means that even if some visualizations are standard, they do not have to be commonplace in the application domain and require more explanation than you might think. Moreover, one expert from the company with extensive experience with the old system used by the company was unsure whether it makes sense to adopt new concepts such as an aggregated representation. At the same time, however, this expert stated that it is possible to imagine that others, especially younger people, would use the system frequently. This is yet another factor to consider when integrating a new tool into an existing system. While the heat map is obviously suitable for aggregating the data effectively and providing a general overview, exact comparisons of overlapping areas are still somewhat difficult. Therefore, we have applied the considerations of Gleicher et al. For visualizing comparison, and used the comparative design juxtapose, which we implemented as a multiple coordinated views representation of overlapping polygons. Instead of using just one map, the available space is used for displaying 4 maps. For example, these 4 maps have the same size and show the same area at the same zoom level. Thus, the multiple coordinated views representation adheres to the guidelines introduced by Baldonado et al. For using multiple views in information visualization. Instead of displaying all categories on one map, they are distributed across all maps. Then, Each map contains different information which follows Baldonado's rule of diversity. As the data is displayed the same way on all maps, the representation remains consistent, which is stated by the rule of consistency. To examine the map section in more detail, zooming and panning can be used, while both techniques are performed synchronously on all maps. This way, all maps are coordinated with each other. However, this does not yet simplify direct comparisons that much, especially since the data is no longer displayed on the same map, and thus the cognitive effort is higher due to the higher distance of same points on the map. But to help with that, the mouse position is symbolized by a cross on all maps, except for the map the mouse is over. This helps to find the exact position in each map. In addition, we follow the rule of self-evidence, because brushing is used to highlight selected areas on all maps. So a polygon can be selected by clicking on it with the mouse. Then, the polygon will be marked as selected with a thick orange border and a striped texture. At the same time, it is also displayed in this way on all other maps, even on maps where the corresponding category was not selected for display. This supports identifying any overlaps. If a polygon has been selected, all available information is displayed in an information panel. As with the heat map, we store for each polygon which others it overlaps with, and this listing can be viewed in this panel. To visually examine this overlap, the corresponding element can be selected for display. Then this element is also displayed on the map and has a vertically striped texture. This way, you can see exactly where this element is located on all maps and how it overlaps with other polygons. This approach fosters analyzing the differences and the commonalities of 4 categories, or combinations of categories, by assigning them to one of the maps, respectively. This allows for determining other polygons a certain polygon overlaps, as the environment of the target area can be examined. Furthermore, it can be checked whether or not different polygons overlap perfectly in a certain area, because the exact position of the polygon is shown. Again, the usability study showed very good results. Unlike the heat map, there were no comprehension problems here. The multiple coordinated maps were received very well by the experts and pointed out as particularly helpful. As some time has passed between the submission of the paper and today, we have continued to develop our tool, and now I would like to give a brief preview of what else the system can do. As mentioned at the very beginning, the renaturation process produces a large number of documents that contain important information. However, this information is rarely available in digital form, and in order to use it, it must always be read in its entirety, which takes a lot of time. However, specific restrictions can be found in the documents such as, slopes must be protected against the effects of the weather, or native species of bushes must be planted on the slope to stabilize it against rupture, or forest operations are forbidden during breeding season. What we were able to show in another paper is how we can digitize these documents, including some that are already several decades old. This was made possible by a combination of an optical character recognition and a text classification used with an active learning approach. This helps us with the following problem. For example, there are instructions in the documents that depend on weather conditions and are particularly important for the safety of the workers on site. An example for this is, driving on the roads with heavy vehicles is not allowed during heavy rain. In order to be able to process this sentence, it is first necessary to define what the term heavy rain means. Then, a source must be included that provides legally secure data on the weather with which the term can be matched. Our system is then able to automatically link the areas shown on the map with the associated documents and restrictions, and check the validity of the conditions using current weather data. This then looks like this. For a certain date there was a heavy rain event and our system displays the corresponding data and automatically highlights the area for which there is a valid restriction. It also shows the exact values, so everything can be understood exactly. Finally, there are temporary restrictions. For example, no hedges or trees may be cut down during the breeding season of birds. Our system can also present this temporal data well for the user. To come to the end of my talk, I'd like to summarize our findings. What I have shown here is how to represent massive amounts of data, especially geospatial data, to make overlapping areas visible. On the one hand, We achieved this by aggregating the data using an interactive quad tree and displaying it layer by layer as a heat map. On the other hand, we simplified the problem by removing the distortion of visual clutter through the use of multiple coordinated views on which the individual polygon layers are divided. Finally, a usability study showed that our system solves the problem well and that our tool was well received by the experts. Thank you for your attention.